Modern artificial intelligence writes fluid prose and generates breathtaking art. But ask it to process exact structural mathematics, and it often falls apart. The reason for this blind spot comes down to something called an inductive bias. This is the internal spatial structure, the literal geometric shape a computing system uses to process information about the world. Classical neural networks operate in a continuous, flat Euclidean space, but exact math, like the modular arithmetic used on a clock face, is inherently discrete, circular, and periodic. The internal shape of the AI does not match the actual shape of the problem. Because you cannot neatly map a looping circle onto a flat, infinite grid, classical AI models cannot natively calculate these geometric rules. They are forced to guess at them. The tech industry tries to solve this spatial mismatch through sheer force. They push massive amounts of computing power through billions of parameters, attempting to brute force a simulation of those missing discrete rules. When trained this way, models eventually undergo a delayed learning phase called grokking. After hours of failing, the massive network finally discovers a statistical shortcut that allows it to perfectly memorize its training data. But a statistical shortcut is not actual comprehension. When you give the AI unseen data outside its memorized set, that shortcut breaks down. This chart tracks a classical AI learning simple modular addition. The red line shows it memorizing the training data. But look at the blue test accuracy line. Long after the AI supposedly learned the math, its performance violently oscillates up and down. This failure scales up. Here is a chart showing the same classical model attempting to learn a highly complex set of spatial permutations called the S4 group. Even at the very end of training, we see that same high-frequency instability in the blue line. Grokking gives the illusion of intelligence. In reality, it leaves the model vulnerable to erratic predictions and logical hallucinations. Researchers at the University of Illinois have developed an entirely distinct computational architecture, the Universal Quantum Transformer, or UQT. Instead of writing software to simulate mathematical rules, the UQT uses quantum physics to physically embody them. To understand the efficiency of this approach, we have to look at its scale. The UQT doesn't use billions of parameters. It operates on a microscopic substrate of just 5 qubits, utilizing only a few hundred parameters in total. Classical models process data using dense attention matrices. The UQT abandons this entirely. It takes input tokens and embeds them as specific rotation angles directly onto a physical quantum state. Because quantum waves naturally rotate, combine, and interfere with one another, their physical movement cleanly mirrors the cyclic, looping geometry of exact mathematics. By operating in a space that natively matches the shape of the problem, the UQT bypasses the massive parameter bottlenecks that choke classical AI. This physical alignment yields a state of learning strictly beyond grokking, crystallization. Crystallization occurs when an AI model completely stops statistically guessing. It reaches a state of deterministic stability, where its predictive variance drops to absolute zero. We can see this in the data. This chart shows the UQT taking the exact same modular addition test that broke the classical model. The blue test accuracy line doesn't oscillate. It locks in at exactly 100% and remains perfectly flat. The results are identical for the highly complex S4 permutation task. Where the classical model violently fluctuated, the UQT jumps sharply and crystallizes into a completely unbroken horizontal line. A flat line like this proves the UQT hasn't memorized a statistical pattern. It has physically locked into the exact mathematical symmetries of the rules themselves. Proving a concept inside a pristine, simulated digital environment is one thing. Physical reality is much less forgiving. Current quantum processors operate in what's known as the NISQ era, meaning they are highly sensitive to environmental noise. The qubits rapidly suffer from decoherence, losing their quantum states to the surrounding chaos. The viability of the UQT depends on whether its wave interference is strong enough to survive the chaotic degradation of actual physical hardware. To find out, the researchers took their parameters out of the simulator and deployed the UQT directly onto physical IBM quantum processors. Despite severe, unmitigated hardware noise, the architecture successfully processed the logic. Across 30 evaluations, The UQT achieved an overall 96.7% success rate, scoring a flawless 100% on every single unseen generalization test. The geometric structure of the UQT's wave interference was so inherently stable that it cut cleanly through the machine's random noise floor. If we want artificial intelligence to flawlessly execute formal logic, we do not need to endlessly scale trillion-parameter monoliths across flat digital spaces. We need models built with the correct physical shape.